Hi guys, hope all of us are doing great. My name is Ernest and this is Ernest Sciences and Mathematics TV channel. In my channel I deal with the different aspects of mathematics, physics, chemistry and biology. And today we are going to look at a concept in definite integrals, and that is the Riemann's sum. Now the concept of a Riemann sum is going to assist us, of course, find some of the applications of a definite integral, especially on the concept of areas. And in this, of course, we're going to look at specific ways in which we can be able to visualize different points which are, of course, falling under the category of the Riemann series. So in this specific case, I'm going to use a series of illustrations which are going to assist us basically try to appreciate the work of this German mathematician by the name Bernhard Riemann. Bernhard Riemann, in some of our discussions, we are going to come across one of or a number of his applications, whereby we're going to see that his work contributed heavily, especially in the different areas of differential geometry and some other aspect of physics. We are going to look at the concept of a number theory. So in this case, of course, in order to appreciate his specific contribution, we're going to look at a geometrical interpretation of this specific aspect of the Riemann series in two sets. So the first set, I'm going to just discuss it in this specific video. And I'm going to do the second one, of course, which is a geometrical interpretation of the Riemann's, as of course, the sum under the concept of definite integrals. Now, in this specific illustration, I've just given a range of values for the closed interval between A and B, and these are going to be x range of values between x and 0 to xn, whereby we're going to give n as a positive integer. Therefore, I'm going to use this specific illustration for illustrating that. So if we try to compare this specific range of numbers for this closed interval A and B, we are going to create a decomposition, or rather try to create subdivision, sub-intervals of this specific range of values, which are going to be numbered as x1, x2. At this specific point, they are going to proceed to xn, but I can be able to choose just a specific partition at this specific center for a kth value, which I can give as xk. Now, to define the difference between the xk and the previous of course, division for k, we're going to have it as k minus 1. Of course, and the difference between the two, therefore, is going to be given as xk minus xk minus 1, given as such. And this is going to give us the length of this specific division for delta xk given as such. So, using this specific approach, then therefore, I would like us to look at this specific discussion from that particular perspective. Then therefore we're going to have a range of divisions whereby the sub intervals are going to be demarcated perhaps using the x from x0 to x1 given as such, and then we're going to have x1 to x2 given as such, and this is going to proceed in that specific order up to the final one, whereby we're going to have x. Of course, this is going to be xn minus 1 and x given as such as those sub-intervals of this division for these closed intervals from A to B. Now, I've said that, for instance, we're going to see that this can as well be illustrated for these specific numbers, whereby we're going to see that the closed intervals A are going to range between this specific value for x1, x2. These are equality signs I'm putting at this specific center, so they note that x1 is greater than, so they proceed in this specific respect for x2, and this is going to proceed on until we reach a point whereby we're going to get this last one being given as n as such, and this is going to be equivalent to b. So basically this means that a1 is equivalent to x0 and b is equivalent to xn given as such. So the length of these specific divisions can be given as a general illustration that are given for delta xk, which is equivalent to xk minus xk minus 1 given as such. So this is the length of this specific interval that I've given for such. Now suppose we have a function that is defined on the closed intervals a and b, which can be, of course, a partition of that specific interval. We can be able to describe a function that is going to be of the form of an expression, which I'm going to show on the board. But before we look at that, I'm going to look at a specific aspect that is going, of course, to assist us try to figure out which, or rather what this specific Riemann sum entails. So in summary, I've said that we have a closed interval which is ranging between A and B, and this is going to be given in a form of sub-intervals which are going to be given as in terms of x, and this x we can be able to find the length of this sub-interval by finding the difference between this sub-interval. For instance, I've given for k, so therefore I'm going to give it as delta xk is given as xk minus xk minus 1 given as such. And then I've said that from this specific part, we can be able to equate A as the initial point of that specific closed interval, and therefore B is going to form the last bit of this specific interval, whereby n is a positive integer, as I've said. Now we can be able to again introduce another factor that is going to be considered in this specific kind of a sum, whereby we are going to see that there's going to be a large interval. As we said, these intervals are not necessarily going to be the same, so we can have a variation, or rather the different lengths for this specific interval, and therefore we can be able to denote those specific intervals using various, this is for delta x1, delta x2, and then this is going to go on up to a point whereby we're going to get the last one being given as delta xn. And this is going to be the last one. If we try to look at this range of deltas, as I've said, they necessarily not have to be the same. There's going to be the largest difference of this specific delta in terms of maybe length. So this largest sub-interval is going to be denoted as P, with those specific strokes that refer to the concept of norm. We have talked about the concept of a norm in vectors, and therefore this is going to be referred to as the norm of the partition, which is going to be given as P. So therefore later on we're going to see that in the application of these specific divisions in trying to find perhaps area under the curve, they're going to have an effect, in a sense that for the value of the norm of P that is going to vary, of course, as I said, from this specific case for the maximum change or a maximum interval, for the value of P to vary, of course, which perhaps is going to be either large or small, we're going to see that that's the closest approximation to that specific area under curve that we're going to encounter, and that is going to, of course, give us the concept of a limit, but I'm going to give that one using another form in our next discussion, as I said, for the geometrical interpretation of this specific sum. Now, therefore, from this specific discussion that we have had, so if we have a function that is going to be defined on the closed interval, therefore we can be able to have let f be defined on the closed intervals of AB, given as such. And then therefore we are going to see that this specific division that I've given for the partition of P can be represented as P on that specific closed interval. So this is going to denote what we refer to as a partition on that specific closed interval. And therefore we can find a relationship between this by giving it in terms of an expression, whereby we are going to give it as a function of x for P. So it's going to be given as a function of fx for the partition of P, which is going to be in the form of Rp is equivalent to the summation from B is equals 1 to n. So we have said that this n is going to represent an integer value which is a positive, and therefore we're going to have this one represented as f wk and change in k. Of course, I'm going to elaborate on this specific expression. Now, R is going to represent the concept of a Riemann's sum, And of course, this summation sign from B is equals 1 to n f w k and change in k given as such. So this particular initials that I've presented in this specific case are going to be more elaborate. But of course, we have talked about the concept of change in k. And in this wk is going to represent any point that is going to be, of course, given between this specific partition. And specifically, we're going to see that we're going to give the values of a central point. So if you have a function, for instance, that is going to be given in the xy coordinates subset. So if you have a function like this, and then we're going to partition this one in terms of rectangles, and at this specific point, which is going to be a center, perhaps, we are going to give the value of wk given as such. So this is going to be more elaborate in our second discussion on the geometrical interpretation of the Riemann's sum. So in this case, I hope that this is going to give us a rough illustration or interpretation of this specific function for the Riemann sum. And for this particular value, I've said is a value that is going to just be given in between, that is going to be given and at the end of the points in between this specific range over delta xk at end of the partition is in between here. So this expression basically represents the Riemann sum, which is one of the applications of definite integral. So catch us in our next video as we're going to look at this specific concept of a Riemann sum in an exclusive way. So that is it for now, guys. Check in our description box for the links of various videos on the same. So that is it for now, guys. Bye. God bless you.